Assalamu alaikum students. We are going to learn the lecture number 36 from chapter number 6, which is fluid dynamics. Today we are going to learn about equation of continuity and Bernoulli's equation. First we learn about the equation of continuity. Let me see. Equation of continuity. Equation of continuity is the product of cross-sectional area of the pipe and the fluid speed at any point. Area is written with A and the speed with V. The product of area and speed equals constant. This constant equal to the volume flow per second of the fluid or simply flow rate. Equation of continuity is that the product of area and speed which is equal to constant, and this constant equals to volume per second. It means volume per time, or it is also called the flow rate. The mathematical expression of equation of continuity is this: product of area and speed at a point A will be equal to the area and the speed at a point 2. These two terms is equal, that's why it is constant. Here we are taking the case of an ideal fluid. Next we see the diagram of equation of continuity. We are taking the pipe of different cross-sectional area. When the fluid at a point 1, it covering a distance delta x1 and moving with the velocity v1, and its total area is a1. When it go another point 2, here its distance is delta x2 and moving with the velocity v2, and its area is a2. Before going to derive the equation of continuity, we discuss some its key points. We know the equation of mass equal to product of rho into volume. When we find the equation of rho, then volume is here multiply it. When it goes to another side, it divides with m, and the value of rho become rho equal mass per volume. Here we are taking an ideal fluid, that's why its density is constant. So we can also write rho 1, rho 2 equal rho, because density at a point 1 and density at a point 2 remain constant, because this is an ideal fluid and it is its property. We know that the volume equal length multiplied by width multiplied by height. So product of the length and width is also equal to area. So we write here length with area and x as it is. Come to distance equation, s is equal to vt. When we replace s with x, then it become x equal vt. In equation of volume equal a into x, when we put x equal vt, then it become volume equal area multiplied by velocity multiplied by time. Equation of continuity, it also called the law of conservation of mass. For an ideal fluid, the mass entering from one end of the pipe will be equal to the mass leaving from another end of the pipe. It means the mass at a point 1 will be equal to the mass at the point 2, because equation of continuity is also called the law of conservation of mass. So we can also write that delta m1 which is equal to delta m2. We know the equation of mass which equal m into rho 1 v1 delta m1. For when we put volume which is equal to area multiplied by distance, and distance equal to v into t. So when we put x equal vt, then it becomes rho 1 a1 v1 delta t. Similarly for second mass, we write the same equation but here with the term 2. Then we compare both equation 1 and equation 2. So we are taking a condition of an ideal fluid, so its density is constant. So we write rho 1 rho 2 with rho. and it cancel with each other, and delta t is also same, so it also cancel with each other, and we get a1 v1 equal a2 v2, which is equal to constant, which is the equation of continuity. At a point 1, the product of area and volume velocity is same. At a point 2, it is same, it means it is constant, so it proved. And the second term is that product of area and velocity equals flow rate. As we know that the dimension of area is meter square and dimension of velocity is meter per second. So when we rearrange this m and m square, it become m cube. So m cube is the dimension of volume and second is the dimension of time. So it become volume per time, which is also a flow rate. Next we are discussing the Bernoulli's equation. First we see its definition. For an ideal fluid, here we also taking a case of an ideal fluid. The sum of pressure, student, you are familiar with the pressure term, kinetic energy per unit volume and potential energy per unit volume remain constant. For an ideal fluid, sum of pressure plus kinetic energy per unit volume plus potential energy per unit volume remain constant. You are familiar with the term of pressure, but you are not familiar with the term kinetic energy per unit volume, potential energy per unit volume. So we check its key points and understand these two terms. We know that density equal to mass per volume. And we know the equation of kinetic energy, which is equal to 1 by 2 mv square. When we divide the both side with the volume, then it becomes 1 by 2 mv square over v, and kinetic energy also divided by v. When mass over volume, it becomes rho, so we write here 1 over 2 rho v square. Similarly, when we divide the potential energy with volume, it becomes rho into g at. So here we write pressure plus kinetic energy per unit volume plus potential energy per unit volume, which is constant, which is a Bernoulli's equation and its condition. Now we see the diagram of Bernoulli's equation. This is a ground and this is a pipe of different cross-sectional area. This is a point 1, upper side of the pipe and the lower side of the pipe. Upper side at a height h1 and the lower side at a height h2. When the fluid at a point 1, here its displacement is delta x1 and its mass is delta m1 and moving with the velocity v1, and here exerting a pressure is p1, which is in the direction of fluid flow. When fluid come on the point 2, here its mass become delta m2 and its covering distance is delta x2 and its velocity become v2, but here the pressure of fluid is opposite direction to the fluid flow. So at a point 1, work done is positive, and at a point 2, the work done is negative, because here pressure is exerting in the same direction of fluid flow, but here the direction of pressure is opposite to the direction of fluid flow. So here velocity change, height change. That's why we also see the change in kinetic energy, change in potential energy. So you remember these two equations. The rate of change of kinetic energy equal 1 by 2 mv2 square minus 1 by 2 mv1 square at a point 2 and at a point 1. And change in potential energy at a point 2 minus at a point 1. Now we calculate the work at the upper end. At upper end, the pressure and the direction of fluid flow is same, so here is work is positive. We know that the equation of work equal force dot displacement. When dot, it become Fx cos theta, and F equals P into A. So are we calculating a first work at a point 1, so we put F1 and delta x1, and then F equals P1 A1 into delta x1. Now we will calculate the work at lower end. The work at the lower end is negative because the pressure and the fluid direction is in opposite direction, so here work is negative. We write the same work with the point 2 and put a negative sign because here work is negative. Now we calculate the total work. Total work equal upper end work plus lower end work. We put the value of W1 and W2 and then write this. We know that X equal Vt. Similarly, X1 equal V into delta T1 minus P2 A2V into delta T2. From equation of continuity, we see that the product of area, velocity and time equal to volume. So put here we volume and also put here a volume. Volume is a common in both, then we take it common. So equation of total work becomes P1 minus P2 into volume. Now we put the total work equal change in kinetic energy plus change in potential energy. Total work is equal to P1 minus P2 into total volume, and change in kinetic energy equal 1 by 2 mv2 square minus 1 by 2 mv1 square plus mgh2 minus mgh1. We know that equation of volume equal m over rho. So m is common is here, so we take it common from all equation, then it cancel with each other and the equation become P1 minus P2 into 1 by rho into 1 by 2 V2 square minus 1 by 2 V1 का square plus GH2 minus GH1. Rho is dividing here, but when it come on the another side, then it multiply with all equation. So it become 1 by 2 rho V2 square, which is also kinetic energy per unit volume, and it become 1 by 2 rho V1 का square. It is also kinetic energy per unit volume at a point 1 plus rho GH2. It is a potential energy at a point 2 sorry, and this is a potential energy per unit volume at a point 1. Now we took the equation of point 1 on one side and equations of point 2 on another other side. We see that the sum of pressure, kinetic energy per unit volume, potential energy per unit volume equal to the sum of pressure plus kinetic energy per unit volume, potential energy per unit volume at a point 2 is equal. It means it remains constant. So we write the general equation: pressure plus kinetic energy per unit volume plus potential energy per unit volume, which is constant, which is the Bernoulli's equation that is proved. Thank you so much. Allah Hafiz.